All right, very good. So let's try. So this is the deck design. This is the. So after we gave the, we understand the history, the LRFD concept. We talk about the live load and the different load combinations, and then we talked about the distribution factors. And now I think these are the background that you need to start the first design. And what would that be? Well, that would be the deck, because the deck is the first thing you would probably design, so that you have all the information when you are designing the girder, and you need the information from the deck. So this one, I think I would like to thank my student Chan. She helped me in putting this together. We teach this in the class, but I think we consolidated it, and we took one example. There are many examples online. I think we will share with you, maybe towards the end of the day, we'll email you the link to some of the examples. But I used the Federal Highway example. It was done in 2005 and now updated in 2015, but we updated it so I want to acknowledge that, and I want to thank them for whoever, I think M&M did it and Michael Baker did that, some part. So we did update it, excuse me, to the 2020 specs. So what you see here is basically the approach taken by AASHTO to do a deck design. And we tried to also look at what NJDOT in the Bridge Design Manual, the 6th edition, we tried the older one, not the new one. We tried to also be consistent with that. So we're showing you that. So in AASHTO, there are mainly, AASHTO allows you to do the design of the deck in 3 different ways. One is the traditional, or what's called the approximate method, or what has been based on what some people refer to as the equivalent strip method. So like slabs, normally you take a strip of that slab, 1 foot a strip. Here the strip might vary if it's in the positive moment region or in the negative moment region. That's the approximate method. And then the other one is the empirical method, which came about as a shortcut, at that time, to doing the approximate method. Because the approximate method, you are dealing with a continuous beam. It's a beam on elastic foundation, meaning beam. I mean, it's a strip of slab sitting on the girders, and the girders are assumed to be rigid enough. Therefore, that slab, that strip, is considered a beam sitting on supports, and the supports are represented by the girders. So that was the idealization of that concept, and that took time. If you have a slab of 4 bays, 5 bays, 6 bays, you would have to analyze them and get the exact answers for that. You would have to use the influence lines, and it wasn't that simple. So people said, well, I don't want to do that if I can find a quick way to do it. And in the early 70s, there has been a lot of research done on the fact that the slab between the girders, especially if the girders are closely spaced, that the slab, when you apply a load on it, it doesn't behave as a flexural member only. It behaves as like an arch, because there is this compression. Apply the load from the thickness of the slab, you would go to the support, and then that would be kind of an arching action. And that arching action was justified by the fact that, well, the bridge decks are surviving and they're behaving, and there were a lot of fatigue studies done. They cycled those, and they seemed like fatigue is not an issue, and therefore and people came up with equations. What are the contribution of arching action? And on that basis, people said, okay, if the bridge has certain qualifications, meaning the spacing, the thickness, the number of girders, etc., you are able to use this method, because then you can get an additional capacity from the arching action, and thus the reinforcement, what you use for the reinforcement, should be standard. And many DOTs use that empirical method. And then the last approach, if you have a complicated bridge and you would like to have these methods do not lend themselves, with the assumptions they're making to the case you have, you could always do a finite element, a more refined analysis. So AASHTO, if you notice, everywhere AASHTO allows you, says, okay, this is the minimum standard, but if you want to, go beyond that, please help yourself. But yeah, you got to do it with a certain, constraints. And that's what we call the refined analysis. We're not doing that here, but we're going to take a deck example and we're going to try to do it in both ways and see what the outcome would be. So let me go here next. So for the, still it's not moving. So here we have a deck design, and basically we're taking as we said, the strip. Okay, so we look at the green is the positive moment region. So you got to design for that one because this is where the slab will be behaving. And then you have to look at the negative moment region. So it will be something like this. Okay. So in the negative moment region, you would have to worry, excuse me, about the reinforcement, top and bottom, and the design outcome. What AASHTO will give you is the thickness of the deck. You will talk about the primary reinforcement. And what is the primary reinforcement? It's the reinforcement, for example, in the bottom. This is the primary reinforcement. It's pointed out here because that's where the tension will be in the slab when it bends. It will bend in this direction. So that will be the bending. To take the bending in this direction, you need that primary reinforcement. You will have also the distribution reinforcement, so that because the bending is in one direction, right? Between the girders is two-way slab, but you also have in the longitudinal direction, you also have bending. If you look at the with the traffic, so this direction here is perpendicular to the traffic, right? So there's bending between the girders, but there's also along the traffic direction, there's also some bending. So you need to have this distribution reinforcement. And if you have a negative bend, this is the primary reinforcement here. For the negative moment region, you would have to design that. And you would have on top, because mainly the sun and the radiation of the sun and the thermal temperature reinforcement, and in the early age, most of the shrinkage, the girders below will not shrink, but this one will shrink. So there will be some shrinkage and some mainly temperature thermal stresses on the top starting. So there will be some temperature gradient between the top and the bottom. So you need to have what we refer to as temperature and shrinkage reinforcement. This is very empirical. There hasn't been a actual design for that. So it's chosen as a percentage of the main reinforcement. Okay. And then you are done with the reinforcement of the design of the deck. So let's see how this works out. So the given in the problem is a bridge. This is the same bridge. We're gonna deal with it later. We're gonna be using a bulb T, a PCI bulb T, 72 inches deep. And the girders are spaced at 9 feet spacing. We have 6 girders, and the roadway width is about 48 feet. The overhang, is about, from the center line of the girder is about 3 feet, okay? And the number of lanes, we're talking 4 lanes, and the concrete girder strength is given. It's a pre-stressed concrete, so we're giving you the initial transfer, and the non-pre-stressed reinforcement, the pre-stressed reinforcement, and also the I don't see the slab here. The slab, I believe it's made of 4,500 psi. Maybe in the next slide. Yeah, it's 4,000 psi here. Okay. We're gonna use top cover as 2.5 inches, the bottom cover 1 inch. Okay, this is in the bridge design manual. This is your requirement, and and you have also a table here. One thing about the old table, I think this is the time when we did that was, I think metric was going to take over in about 2000 or so. There was a lot of push to do everything metric, and everything was converted, soft conversion. So this number 16 is nothing but number 4, and number 5, number 19 would be number 6, in the U.S. customary units. This is in the metric conversion. So the tables in the manual are still like that. One suggestion that I would do is to, since number 16 and 12 inches, I think we should go back now, since that metric is story of the past. We should go back and update this in the manual to keep them in also the designation, the U.S. customary designation. So this is the table that was done, I believe, and we redid that for the new design manual. It was done based on the approximate method, on the traditional method. And, the spacing here, I don't know at that time why they used the 4 feet 3 inches, not 4 feet, for example. I don't have an explanation for that, but anyway, these are for certain spacing. Let's say you are here, and with the slab thickness, you require it to be 9.5. And then so this would be already done. You pick it up, and you don't have to do anything else. So this is one way. The other way is to look at the AASHTO requirements, and for you to understand what. So the AASHTO says a minimum thickness of a deck cannot be less than 7 inches, and the thickness, we're going to have it here as 8 inches, and we're going to have a sacrificial surface of 1 inch. Usually it's 0.5 inch. In this case, I'm sticking to what the Federal Highway example. So if you download that, you will have it. So you will be able to match what we have done in more details here. There is no deck design in the Federal Highway example. So this is what we have done. And for an overhang, they also put a limit. So obviously, and the overhang, here in this 3 feet, it cannot be more than 50% of what the girder spacing is. In other words, I think limited to a certain length. I don't remember how much that, but it cannot be. You cannot have a very large overhang because that will be even if you have a sidewalk, you cannot do it that way. You have to make it a hunches. You have to make special design for that. So for the dead load, if we start again, we want to calculate the dead load. Okay, how much would that be? So you have to make sure you take them as the cast in place versus the barrier. This one and the wearing surface. Okay. So the wearing surface, might be different in a future wearing surface. So you have to accommodate for that. Okay. And so here we have the the unit load for each one. So this is in the positive moment region, and this is in the negative moment region. Okay. So this is the dead load, and they're all uniform load, right? Dead load here is done as a uniform load. So for the live load effect, okay, for the live load effect, you will have to use, there are, again, 3 methods as we did earlier. AASHTO LRFD table 41A, or the equivalent strip, or the finite element. So let's go first with the approximate method, which is the equivalent strip. So the AASHTO says, when you are trying to find the strip of the slab, you would have in the positive moment region, for the interior, you would have to use this here, depending on the girder spacing. Okay, so it's not a 1 foot thing, like we do in buildings. You take a slab 1 foot because it's uniform. Here, each one is considered, a different strip. And the negative moment region, you have this equation that you would have to use. Okay, so here, in the positive, maybe the strip would be this wide. Let's say here it might be a little bit more bigger than that. Okay, the strip in the longitudinal direction, and you can see here the moment, divided by the equivalent strip times the impact factor times the multiple presence factor. Okay, and this is the table A4 you can do that from this method one by looking at this table. So for example, our spacing is in this case it's you don't have I think this is 8 feet, we should use 9 feet instead of 8 feet, right? Spacing between the girder is 9 feet. So this is 9 feet here, right? So if Chan is here, I would like to ask her, why are we using 8 feet? But anyway, Chan, are you there?
Yes, hi, Professor. Yeah, so our design are targeting at a girder spacing at 9, and because we wanna put all of the both methods 1 and method 2, so we just illustrate an example here to say how do we select the moment based on the girder spacing here. So 8 is an arbitrary number here.
Okay, but the table has 9 foot spacing.
Yeah, right? The table has a lot up to maybe 10, right. 13 or even more.
Should pick up for 9.
Professor.
Yes.
I think in a design manual, we are using 8 to 10 foot spacing. I mean, you know.
In this table, you mean, or?
No, in the design manual.
Is
this from our design manual?
Yeah, this table, this is for the empirical method, I believe. I mean, not the empirical method. This is for the selection. Yeah, this is from your design manual, so you are using.
It's a recommended spacing.
Okay. Right. So I would say, I mean, here you get you're already designed for it, so it's already done. You know what I mean? And I say number 5 at 8.5 inches. If you do it exactly, I think we got number 5 at I believe 12 inches. But this ASHTO table, okay, I think it has more. If you look at it, it has more, so you can get it exactly for 9 feet. But I think Chan was illustrating the method. So for 8 feet, you would get the positive moment, what the positive moment load that you're gonna be using to get the moments and the shear. Okay, this is mainly for the positive moment, and for the negative moment, depending on the distance, from the center line of the girder to the line of the section for negative moment. So there are, different ways of doing it. So this is the method 1. Using
Professor, before you can I hear once more?
Yeah, let's go ahead.
Okay, can you go to your previous where you show positive and negative moment transversely?
Oh, you mean here?
No, there was a diagram that shows. Well, you draw it up, but anyway, I just want to let our young engineers know that when you're doing your design, just one thing, this one right here. Yeah. When you are doing your traffic control staging, just make sure that when you're using those construction barriers, not to pin the construction barrier type C. Now we're going to have a type D with 0 deflection, not to put those pins on those negative moment areas. Because if the pin cuts any of those top mat, especially the transverse, you could compromise the deck.
Right.
So I just want to let our young designers know to keep that in mind, that when you're doing your traffic control staging, it's important to remember that the slab is like a continuous multi-span between the girders, and the negative region is mostly on where the girders are. So not to use those. Well, we don't allow pinning into new decks anyway.
Right.
So that's something that people should be aware of.
That's a good practical observation, Ali. Thank you. Okay. So let's go back. So basically, what these tables will help you, it would give you, or you can, based on the strip method, if you use the strip method, based on each strip, you can get what is the weight. I mean the kip feet per feet, the moment per kip per linear feet based. Based on this equation, where the impact is the impact factor, okay, and M is the multiple presence factor. And I believe the impact here, for decks, you would have to use the 0.75 to 75% Chan. Is that correct?
Correct. 33%.
Right. And about the multiple presence factor, depending if you loaded with one truck or two trucks, correct?
Yes.
Yeah. So this way, if it's one truck, it's 1.2. If it's two trucks, it's 1.0, and so forth. So because you could place here, what we do is you could place one truck here, let's say, and then do another, 4 feet spacing, and then put another truck. Okay. So it might be that in the same spacing, it might be putting more than one truck. So the positive moment for single lane will be different than when you have two lanes. Okay. So this is looking at the truck. This is the two wheel load. This is the 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 wheel load, right? So for the deck design, you can see that it's not the whole truck. I mean, the whole truck is involved, but it's mainly the axle loads are what's going to be controlling the moments and the shear, right? In a girder, you can put one truck and then follow it by one truck. The whole girder will deflect under the effect of them. But here, it's the axles. And some of the axles, if you're taking the strip here, there will be some, if the truck is like the HS20 truck is about 28 feet, some of the loads they will be distributed back to the strip because they have some effect on the strip. The fact that they are in the long direction, but you still have to take them into account. But the loads here are the 16 kip each. So 16 kip, and then you have 16 kip, and then 8, the 4 kip and 4 kip for the front axle, right? So in a way, the deck design is controlled by axle loads. That's what it is. But the axle loads are light for HS20. Notice that for the girder, as I said earlier, you are designing for HL93, which is the axle loads from HS20 plus the uniform load. In the deck design, we're not using the uniform load, right? So that's why, and this is the Chan's thesis now, is about, we think that deck should have its own limit state because the loads are underestimated. Because the axle loads and the WIM data, we're seeing them even twice as much and 3 times as much with the tandem and the tridem. And this is our legal. Tridem and tandem are legal. Even if they are within the load limit, and so many times they are not, these are, they should be governed by this. And I don't believe that this design governs them properly. The fact that we have arching action, yes, it adds to the capacity. However, the minute you have cracking, shrinkage cracks, or any other types of cracks, the arching action is compromised. You have to have cracks over the support, but if you have a crack in the middle of the concrete, then this arching action is not really reliable, in my opinion. So that's, I think Chan's dissertation is on that. I think she'll come up with very good reliability-based design methodology, because the reason I'm saying this and this point, and I know it's not related to this design, but I wanted you to keep it in your mind, is that the design philosophy for a deck is not giving us the outcome that we want. We design bridges for 75 years. The girders, more or less, they last that long as a service. The service life, people say, well, the service life is not the same as the design life. Agree. But the service life for decks, we have done a study for DOT in 2016. We looked at the impact of the overweight trucks on the infrastructure, and we found out, I think Pang, this was his PhD work, Pang Lu, who's my colleague here, this found out that the average lifespan in New Jersey for a bridge deck is about 36 years, average. So that means there are so many bridges about 20 years, and some bridges are 45 years and 60 years, especially the less traveled bridges. And so ADTT, the number of trucks on the bridge and the level of overweight was a big factor in reducing the lifespan, the service life. So decks need to be more resilient because that's the first line of defense. This is where all the trucks, all the heavy loads are coming in. The job of the deck is to distribute the load to the girders, and the whole bridge should function as one unit. However, we are seeing different kinds of failure. Maybe it's not fatigue, but we're seeing punching shear. We're seeing, that once there's, punching shear, fatigue becomes important. The loads are heavier than what they were about 40 years ago. So we have to revisit this, and that's what we are doing right now. But for the time being, the design philosophy is that you take the slab as a strip, and I believe this is the more detailed method gives you good results in that sense, and you would try to find out what is the moment per linear foot that you need to design. And the load factors, again, so DC1, DC2, and here, DC2 here, it's because the cover is made, the barrier is made the same concrete as the slab. But the wearing surface, assuming it's asphalt, is 1.5. And the minimum load factor, the minimum is when it works again with you, okay, you would have to use this way. And then, you can find the positive moment, if you multiply the factored moment, the dead load and live load, you get about 10 kip feet per linear feet, and the maximum negative moment, you get minus 12.89. And you have to also design it based on service, So based on service limit state, which is the deck cracking, which is strength service 1, and there's also what we call the crack control in a way. So you want to make sure if the deck is going to crack, that the reinforcement, the distributed reinforcement in the bottom are closely spaced. There's a maximum spacing based on the crack width. Actually, the equation in the code is the same as the one in the ACI. In the AASHTO specification, the maximum spacing is related to the crack width, but it's implicitly there. We're assuming that the crack width is the hairline crack is 0.016 inches. That's the maximum crack width. And based on that crack width, you find out what, and you have the diameter of the bar, you have the cover, you try to come back and say, what should be the maximum spacing? So if a crack is forming, it doesn't go beyond 0.016. Because it was found that the corrosion or the ingress of chlorides into the concrete, if the crack is less than 0.016, there will be no corrosion induced into the reinforcement. So that's what this equation is based upon, And it's an equation that ACI adopted it by my colleague Robert Frosch from Purdue, and that was based on a physical model, how the deck will crack the slab and how. So using smaller size rebar with a closely spaced would be a better way to intercept the crack. So don't try to go with larger spacing with larger rebar. Don't go to number 6 and so forth. Try to use number 4, number 5, because that would be a better way to, depending on the spacing that you got, to control the cracking. So this is the service 1 limit state, and the load factors here for all of them are 1, okay? And if you calculate the factored moment for that way, is the actual moments, the service moments that you calculated earlier. Are there any questions up to this point? And then you look at, so we start the design, we let's say, this is the schematic diagram of what the layout of the rebar and the depth of what we, the DS, for the positive moment and for the negative reinforcement and positive reinforcement and the cover. And so in a way, we're assuming a number 5 bar with a this is the D there, the diameter of the rebar, and then you find out what is the moment arm for that one. I mean the depth of that. You get it, by looking at the bottom cover. We assume the 1-inch cover in the bottom, clear cover, and then you can find A A is the beta 1C, which is the from your concrete background. Beta 1C is A with the depth of the Whitney stress block. Okay, so basically, if I do a diagram here, that is basically A. Okay, and this is the neutral axis, and that would be your C. And beta 1 C, beta 1 is a factor that depends on the concrete. If it's less than 10,000 psi, then for every 1,000 psi, you would reduce the beta by 0.05. So it's 0.85 for this, example here. Oh, sorry. And so you find this moment capacity, and you find the area required. So this is nothing but a reinforced concrete. So you get this, and we try number 5. I like round, round spacing, but I think just trying to be accurate here. Oops, why this is doing that? Let me put the mouse distance here. I keep hitting it. Okay, so now this is the type number 5 bar at 10.5 inches for the positive reinforcement. Okay, and you calculate the area provided, and it is a little bit more than what you need, and that's okay. And then you check the maximum spacing, okay, for using the code. So it has some formulation here, okay. It cannot be, it shall not be greater than the lesser of 1.5 times the thickness of the member, which is 8 times 1.5, or maximum of 18 inches. And we are providing, 10.5 inches, I would have done it 10 inches just to be conservative. So you want to make sure, sometimes you get very small spacing, and you shouldn't be getting that. If you get anything very small, you have to make sure that the concrete can go through it, because you have reinforcement in this direction, then you have reinforcement in the other direction. So there are some rules about what is the maximum aggregate size. If it's a 3/4 of an inch, I think, or I think it's the minimum spacing is 3 times, or the I think 10 times the diameter of the rebar. I think the minimum. I forgot what it is, but it should be that way. And then in the so for the positive moment region, so this was here. We started by the positive moment region here, and we did this part. So we're continuing. So check. Now we want to check. You want to check the different. The AASHTO article, the different conditions that you have to meet. Okay, and I believe this is the equation I was talking to about, is if you have different exposure, and this is the maximum spacing. So what AASHTO did different than the ACI is that ACI, the equation is an indoor. So you don't really have aggressive environment like chloride, ingress, and de-icing salts, and so it's subject to the ambient temperatures outside. So there is some more thermal. So that's what they came up with, a different class, that they came up with this factor, and they reduced it by 25%. So that means it's a little bit more stringent, because it's an outdoor performance, right? So to be able to apply this, okay, you would have to calculate, the row. I forgot what this is. This is the what is this, Chan? Is that basically the ratio where the neutral axis is? What is beta as? What do they call it in AASHTO? Do you remember, Chan?
I was on mute. I was muted. I need to check the AASHTO. Let me check.
Yeah, I believe the K factor is about finding the location of the neutral axis. This is I believe this JD and all of that. So this is, you're trying to analyze the the cracking of that section using that model. So basically, for you to apply this equation, you need to find all these parameters and plug them in here to be able to do that. And the minute you get that this is the maximum spacing allowed, okay? Notice that before you were able, for this, you were getting that the maximum was 12 inches, right? That's what, for the, because everyone, for if this is repeated, the flexural capacity has to be maintained, so you need to have a maximum spacing according to Ashton. Or minimum spacing, sorry. This is the minimum of this. So your spacing cannot be, more than 12 inches. So you want to make sure that you have enough. Whereas here, what you're saying here is that if you're putting them too far apart, okay, if it came out that it is, let's say, 12 inches, and with the exposure that you got, to control the cracking, if cracking happens in the bottom, okay, so basically, what if you look at this, mainly it's here, this is your reinforcement. And if there's a crack to take place here, this reinforcement, it will keep the crack closed if they are within 16 inches apart. Okay, so based on the diameter of the rebar that you've chosen, it will give you a maximum spacing that is allowed to keep the control of the crack within 0.016. Okay, so that's the crack control limit state, which is a service 1. And now we do the same thing for the negative moment region. And here you are looking at it in the reverse. So we'll also try to use consistently same type of rebar size and the diameter. And then you can put the D for the negative moment here. You can see it from the dimensions. And you're talking about the center of the rebar. It's not, usually that's why we divide the diameter by 2. So you're talking about the center of the steel and the rebar this is where the force is going to be concentrated. And again, you do the same thing for A, and the capacity is ASFY into D minus A over 2. But now tension is on the top and compression is on the bottom. Whereas in the positive moment region, tension was on the bottom and compression is on the top. So this is a basic reinforced concrete, and then the required is 0.48. Obviously, we can get, for negative moment, we need more. And if we do number 5 at 7.5 inches, then you are a little bit right on the money there, okay, for what's required and what's provided. And the maximum spacing, same thing, we compare to the same limit, and it is less than the maximum. And you can do the crack control also in the negative moment region the same way. And you can see here, it's really very close, for the negative moment, very, very close. That's why you can't go. However, I have a comment here on the negative moment, especially on the right above the girder. This is for right above the pier. I mean, usually this is when you have in the over the girder, right? So you're talking about cracking here, and that can be controlled using this. However, if you have in the longer direction, along this is the slab, this is the girder here, let's say. Okay, and let's say you have a pier here. Okay, then in the negative moment region, you will get something like this. So obviously the slab is going to be, cracking here in the negative moment. This doesn't apply to that. The design here, what AASHTO tells you, in this region, you would have to double the amount of reinforcement, basically, right? Because there's no other, the AASHTO is kind of silent on this, because they're saying that it's gonna crack, and there's not a lot you can do in terms of design, unless you put here some type of, post-tensioning or something to avoid the cracking. But what they tell you is you have to put double the reinforcement so that it can have more life in that region. But if you double or triple the reinforcement, once corrosion compromises that place, it will corrode all the same way. But this is something that there are many details, they call it continuity details, that have been designed to make the slab not crack, basically. So you could do a different post-tensioning technique, different detailing, different allow some link slab that has very high capacity there, or things like that. So this is a different problem than this type of problem. So here the cracking is above the girder. You're talking about cracks that will form in the positive moment region. So there's another. So this is in the transverse direction, but this one here is in the longitudinal direction. So for this situation, this is the answer. Okay, that you have to keep them closely spaced as much as you can above the girder. Okay, and I've seen bridges that have 6 inches also as girders, number 5 at 6 inches also. And then, so now we did the primary reinforcement in the negative moment region. We also showed you earlier how to do the primary reinforcement in the positive moment region. And we checked service 1, which is a crack control. And obviously the ultimate capacity is satisfied because we sized the reinforcement based on that strength 1, right? Now we looked at the distribution reinforcement. Distribution reinforcement is that it's a given as a ratio 200 divided by square root of S, where S is the effective span length, okay? So the effective span length is actually span length, not the girder, but this is span length between the girder, for which the slab is being, spacing between the girders. And you will find that by looking at, assuming the flange, I wish we have drawn a figure here to show you that, but this is, so let's read this. For slabs supported on steel or concrete girders, the distance between flange tips, okay, plus the flange overhang shall be used, okay? In this example, assume a top flange, we had 12 inches and the web size of 5.5 inches, okay? Then you will be, getting the effective S that you need. And then you divide 200 divided by square root of that, you get, this about 69.7, then we can only be allowed to use, 67%. So what is 67%? Okay, is basically you take the area, the primary reinforcement, take 67% of that, and you get 0.24. So we'll use number 4 at 10 inches, okay? And then the temperature reinforcement, and shrinkage and temperature reinforcement is given by this equation, okay? It has to be larger than this, okay? But the value has to be between minimum this and maximum that. And we find that, which is, you need 0.05, so we will use 0.11, okay? And this is for both faces, of the concrete. So for one face, we use, so let's go back. So we are using about number 4 at 18 inches, okay? Now, I think what we mean here by faces of the concrete, it means that if I go back to the Chan, you want to have, so this is, where is it? So this is the temperature for, okay, so top and bottom, you end up doing, so that now the top is 410. Chan, what is meant here by both faces? I don't understand this term.
Yeah, both top and bottom means.
No, but the bottom one, we don't call it, we call it distribution reinforcement, right?
It means that if the distribution reinforcement can cover the amount of the temperature reinforcement, that's fine. But if not, we need to add those reinforcement on the bottom side also.
But I think we had it, the distribution reinforcement was smaller than this. That was number 4 at, let me see, number 4, where is it? Yeah, number 4 at 10 inches also?
Yes.
Okay, so the same, so here intentionally we selected the same, Right. So you have the top temperature reinforcement. It's number 4 at 10 inches, and you would, if the distribution reinforcement that we selected was less than that, we would use that part. And if the temperature reinforcement was less than distribution, we would use the distribution reinforcement. So we try to be consistent in the same, as much as you can, use the same number bar, for that part. So this is the other part is the empirical method, which is, again, it has to meet certain conditions. So these are the conditions that you have to meet. The diaphragms are used at lines of support. Okay, so usually diaphragms are provided maximum every 25 feet maximum, but at the supports you have to have that, especially for the girders to be tied at the support. Supporting components are made of steel or concrete. The deck is fully, here should be fully, sorry for this typo. The deck is fully cast in place and water cured. The deck is uniform depth except for haunches and other local thickenings. The ratio of the effective length to design depth does not exceed 18 and is not less than 6. Core depth of the slab is not less than 4 inches. Core depth is the depth between the top rebar and the bottom rebar. The effective length does not exceed 13.5. So that means, the effective spacing between the girders. Minimum depth of the slab is not less than 7 inches. There's an overhang beyond the center line of the outside girder of at least 5 times of the depth of the slab. And a prime of C not less than 4,000 psi, and deck is made composite with the supporting components. If all of these elements are, then you can use the empirical method, and then you just come up with a girder based on this information. So this is, you would use 4 layers of isotropic reinforcement with grade 60 and above. Outer layers placed in direction of effective length. Okay, so these are the outer layers. Okay, number 4 at 13 and number 5 at 14 below. And bottom layer, minimum AS, give you a minimum that you have to satisfy. And top layer, minimum AS given this way. And maximum spacing is 18 inches. Straight bars only, hooks allowed, no truss bars. Lab splices and mechanical splices permitted. So this is the design. And if you compare what you got here with what you got in the strip method or the approximate method, this is probably about maybe 20 to 30% less steel here than the other one. I don't know if the NJDOT uses this method. I don't think you do. But it would be interesting to figure out. I know New York did some study on that to figure out the performance of decks designed using the empirical method versus decks designed using the, of course, they have to be under the same approximate condition, but if we can get, I believe the empirical method, and we did in the calibration, we worked on that. And we found out that it is a little bit less the life of the or at least the beta involved with empirical.
Honey,
any questions?
yes. So have you ever do the comparison between these two methods? Any difference?
Yeah, we our work when we did the serviceability analysis with my student at the time, Dan Stu. Comparison. We have 2 papers on the empirical method, and we found out that the reliability of the empirical method is lower because the enforcement that you end up getting is less than what the other method provides. This is, I have to admit, this is quicker, but it's not better in terms of design. I think you did also some work recently. We have a TRB paper. Can you comment on that, please?
Comment on the paper?
No. Comment on the behavior of the empirical slab versus the design using the empirical one I wish you did a comparison in terms of the amount of reinforcement. In the class example I have, I believe there was about 25% difference from the total amount of steel. You know,
That much? Oh.
Yeah, if I remember correctly, you know, depending on the spacing that is being used. So here we're using number 5 at 14 inches. Over there we're using, if you remember, number 5 at 7.5 inches and at 10.5 inches. So you can, and number 4 on the top, we're using number 4, I believe, was it 10 inches? So there's difference. So if you talk about, I can give you the quantities exactly. We did it because we were trying to convince AASHTO to disallow the empirical, but I don't think they wanted to do that.
Okay. All right. Thank you.
Sure, you're welcome. Chan, do you have any other comments you want to mention? Did I do a good job on your design?
Yes. Yeah.
Any other comments you want to add?
Just want to comment on the last question. Because the empirical method, they have the constant reinforcement amount despite different girder spacings. However, for the approximate method, the amount of reinforcement varies because of the moment carried by the girder spacing. So with the larger girder spacing, we definitely have larger reinforcement area. So that's the difference between those two methods. And we found that, I think from Dan and Professor's paper, we found the serviceability in terms of the cracking control is kind of deficient in the empirical method because of the large girder spacing, rebar spacing. So that could be one of the difference between two methods.
Yeah, I think here, if you do, and I would like you to look into it, if you do the crack control, you know, it won't be satisfying the crack control here, right? Earlier, when you were using number 5, you were getting that the maximum spacing should be 7.5, 7.6 inches, right?
Mm-hmm.
So if you do now with the service 1, if you use the empirical, you design it, and you check it with the crack control, you will probably, you would have to change this.
Yeah, probably.
Yeah, you know, if I remember correctly, let me show you where you did that. So here, right, you did the exposure. Well, obviously the same number and everything is going to be approximately the same. If you do that, you get 7.6 inches as the maximum spacing to do the crack control. So if you go to the empirical, and that's why in our paper, we realized that at service, this is not good. It's not going to be able to satisfy the service limit state, you know, which is the crack control, the recent equation that was added. So if you do that, then you can default to number 5 at 7.5, 7.6 inches, you know, per se. So it's gonna go back to the design as the other method does. All right, I mean, I'm gonna keep going. I think we'll stop at 12 o'clock because I think this is, lunch is sacred and we need to stop. I know a lot of you are doing it from home, so we would like, and then we can continue after lunch, whatever is left over. So I would like to talk a little bit now. So we did so far the background on the AASHTO, the deck design, and now I'd like to talk a little bit about how does AASHTO incorporate pre-stressed concrete design, okay? I'm not gonna talk about reinforced concrete bridges because, you know, you don't design those anymore. I mean, they're not that popular. You know, you need to understand them, but any reinforced concrete course that you had should give you the proper background. But I think I'm going to emphasize more pre-tensioned, girder design. So for AASHTO, they allow you fully bonded pre-stressing, and for that one, they allow the usual linear plane sections remain plane, which is linear strain distribution. Only if you have a deep girder, like a deep beam, then that linearity and there might be some issues in applying that, and you have to apply deep beam analysis where the strut and tie model would be more appropriate for those type of. But those are very rarely seen. Only on very long spans, longer than 140 feet, you probably get those. The 9 foot, 10 foot deep type of girder. And those usually have problems with the shear because the web has to be very thick. You know, if you use a small web, you end up having some problems with the shear crack, I believe, at the end, especially at the end. But if you make the web thicker, then it's not possible to go that longer span. You'd have to either splice the girder or shore them or do something else. And they used to talk about partial pre-stressing for unbonded, but I think the AASHTO is moving away from partial pre-stressing. A lot of DOTs, they don't like it, and I understand that. European approach is that, so what if the pre-stressed concrete cracks? But here, I think because of our, especially northern tier, is because of the use of de-icing salt, it's understandable that you want the girders to be preserved. You don't want it to be cracked. So I fully understand the New Jersey DOT's conservative approach to, for example, not allowing tension, because the loads in this region are heavier than what the code prescribes to. And enforcement is being done, but it's not really effective all the time. Okay. So for the concrete, the same applies as an ACI. We assume that concrete strain at ultimate fails at 0.003, and that's where the crushing takes place. In many cases, it might be more than that, but that's where we feel that it's not the peak of the stress, but we allow some softening to fail at 0.03. And tension is usually not allowed in concrete. I mean, not counted on, I should say. All right. And the enforcement is, is based on the stress strain curve, but elastic, perfectly plastic. Okay. And I just want to go over some of the provisions in the AASHTO. You probably have seen this in reinforced concrete books, but there is, just to highlight it, so this is a typical reinforced concrete. This is the linear strain. We assume sections as remains plane, sections remain planes after bending. This is the actual distribution of the stress at ultimate, but we idealize it as a witness stress block. And that block, the average stress here, in ACI, we say it's 0.85 of prime of C. However, in many of the bridges, we might have very high strength. We might have girders that are 12 and 11,000 PSI. For that reason, we would use the alpha one and the phi, so beta one, as I say, call it here beta. ACI calls it beta one. So for 0.85, if it's less than anything, between 4 and 8, you take out 0.05 for every 1,000 above 4,000, and 0.65. Because why is that? Because we tested concrete a lot, especially early on. My colleague Professor Nawi, who did a lot of high strength concrete in the early 80s, and we noticed that they're brittle. The softening that happens in 6,000 or 5,000 PSI concrete does not take place really in high strength. It's a very sudden, I don't know if you've seen a high strength concrete cylinder being tested, but it will explode all of a sudden. It goes up and then boom, it will. So there's not much ductility there. Therefore, this is the penalty here. You are reducing the witness stress block basically by putting it that way. And the stress is not always 0.85, the average stress. You are trying to penalize that, especially for high strength concrete. So that's what AASHTO does. So these are the difference between, in ACI, it's usually taken 0.85 upfront of C because most of the concrete is in the same range. Whereas in girders or in, you might be ending using, 10 and 12 PSI. So now and pre-stress, then the reinforced concrete is very simple because you usually have the area of reinforcement, okay? And you have two equations, two unknowns. You have C and T, that's one equation. Two forces are equal to each other. Second equation is sum of the moment. Take about, let's say about point T, take the moment, and you find the moment equation, then you can find the neutral axis, right? And you can find the ultimate capacity of the section. However, if I add another area here, APS, okay, let's say, okay, then you have another T here coming from the pre-stressing, which is equal to APS, okay? In this case here, I have T from initially it's AS times FS, right? The stress in the steel. And that is usually at ultimate, we assume that by the time this reinforced concrete is gonna fail, this is, the concrete will crush and reaches 0.003. This thing here will have reached the yielding. So it's equal to Fy. So I can use this AS Fy normally, okay, at ultimate. However, if you have now an APS in another area of steel, let's say you have APS here, I need to find APS times the stress in the pre-stressing, which is FPS. I need that stress. I don't have that. Okay, I cannot say that the steel is going to be yielding the tendon. It might be yielding. It might reach a value above yielding. Why? Because if you look at FPS, the strain versus the stress, the tendon usually goes straight, linear up, starts yielding, and then goes straight up to about 270. Okay, so the yielding might be somewhere here, let's say. So if this is 270 here, okay, the yielding might be about 230, 235, and then you pre-stress it up to the effective pre-stress, let's say 100, 185, 189 usually. So in this range, it's elastic. But then when you start loading the pre-stressing beam, this stress starts increasing, and we need to know where. We need to know at what value does it fail. Okay, so you need an equation for this FPS, for bonded. And that equation, Ashto is using, this is by the work of Professor Naumann. This is their equation. There have been many equations proposed for bonded tendon, but FPS is proportional to what is the type of tendon you are using, plus KC over D. C here is the neutral axis depth. So you have to find, unlike other equations where they give it as a function of area of steel, area of pre-stressing steel, and the FPE, but they're not accurate. This one follows, a better approach, and they found out the equation, and C over D is the ratio. Okay, C is the neutral axis. K is a factor that depending on what type of tendon they are using, and it's given in this equation. But most of the time, it's usually about 0.28. So if you use 0.28 for stress relief tendons, that would be a good estimate. But depending on what tendon you are using and what is the yielding compared to the they would use that. So this is a very good equation. It predicts the pre-stressing very well. The only thing is that you have to find C first, and to find C, you assume that you are reaching first. So the first value would be, you would say, okay, let's say that it reached FPU, the ultimate, which is 270. You find a value, you put it back in here, you find FPS. Now, in the second iteration, if you want to do that, you go and you put FPS instead of FPU, because that's the true force that is really at ultimate, right? And if you did that a couple of times, you see that it doesn't change anymore. Actually, even if with FPU, you will see that it stays the same. I mean, it doesn't change much, 2-3%. So this is a very good, very accurate equation, and it gives you the strength. For flange section behavior, this is a rectangular section. That means that the neutral axis should fall in the top flange to be, if it's a T section. But if the neutral axis is in the web and it's a flange section, you would use this equation for C. So the same equation up can be used, but this is the equation, the neutral axis, that can be used for a flange section. And this is all in the code. Again, I mentioned here, we made it easy. If you have the code, it will be able for you very simply to go and check it. Now, on the other side, the equation for the unbonded tendon, if I give you the history, because I did a lot of the work on this area, this equation is probably the better equation throughout historically, because it really gave a good estimate. And it's based on the work from Texas Austin by McGregor and Breen, Professor Breen and Professor Greger, Michael Greger. So this work is very good, and they improved it over time. This is for unbonded tendon. Other codes, for example, they say for unbonded tendon, use FPE plus 10,000 PSI. That's it. It's very conservative because there is a fear, okay? And at first, like this here, like a first estimate, you could start by that one. So that's why I would say in bridges, you don't see many unbonded tendons, because when you talk about the capacity, okay, between bonded and unbonded, as a designer, you're going to always go to the bonded one because it's going to give you a higher, FPS. The equations in the code gives you higher FPS, and thus, or not higher, but a value that's, a good prediction of what the actual stress is in bonded. And then when you use the beam, it has a bigger capacity. Whereas in unbonded, the previous equations, or some codes have this kind of equations, they're very conservative. And that's a penalty on unbonded tendon. So when you are trying to design an unbonded section, the capacity will be less than a bonded, and therefore you go with a bonded. So, because a lot of tests have shown that these equations are very conservative, and AASHTO, they really recognize that, and they've tried to basically address it by doing some improvement, and more or less it gives good prediction, this one, compared to the ACI code equation. And again, here is the same way, very similar approach, okay? I think Naaman himself had an equation there, okay, before. However, that equation was changed, I believe, in lieu of this equation, which found to be more along the lines of what bridges behave. Naaman's equation had a different factor. So this is the same way. You find C, So again, here, C, you would have to assume the first round, assume that this is FPU, okay? Again, it doesn't say that in the code. I think it mentions that as in the commentary, but you would assume, find C, put it back here, find FPS, then come back with the value of FPS and put it back here, and then 1 or 2 rounds, and you'll be okay. Same thing with the flange section. So it's consistently a good equation in my opinion, but it needs improvement. And then the approach is the same, that we have to make sure the factored loads are less than the resistance load. So you would look at it from the rectangular section and front section, and for rectangular section, same way. You have FPS now, so you can use this coming from the pre-stressing, the contribution, and by that time, obviously the non-pre-stress reinforcement is going to yield. So and then assume this is FY. It's rare that you don't get the reinforcement. If you reach ultimate, this is a very good assumption. It's very guaranteed, and it will, of course, it will give you more than FY. But for all practical purposes, we assume elastic, perfectly plastic behavior. If you have a flange section, this is the equation that we'd use. Now we estimated the capacity of ultimate. One of the conditions that you had before, if you remember, you need to know, is this going to be a ductile failure? Meaning that what is the amount of pre-stressing, that non-pre-stressing that I'm using? And we did control it before. If you remember, if it was concrete, we had what we call the balance condition, and then you had rho max, which is 0.75, the rho balanced, and you had rho min, which is 200 divided by Fy. So you had many equations to make sure that the section that you are picking is between the minimum reinforcement and the maximum reinforcement, somewhere in between, and that this will ensure that when a failure takes place, that you will have a ductile failure, meaning that the concrete will reach 0.003 at approximately the same time, at the same time when the reinforcement in the bottom will also reach the yielding. So that is a condition that's changed in the LRFD. Now, because we have everything in terms of C and D, I think Naaman came up with what he called the effective depth of the reinforcement. So when you're looking at it as a structural concrete, you don't care if it's pre-stressing or if it is non-pre-stress reinforcement. You treat it with a center of tension. contribution of it is from the tension. The tension force is a combination of contribution from the non-pre-stress reinforcement and the pre-stress reinforcement. So that D effective is basically the center of the force of the steel, not the center of the steel. There's a difference, in the notation sometimes. This is the center of the force where the tension force is applied, because that's what you need to care about when you're finding the moment arm and the capacity. And at the same time, he came up with this condition, which is C over DE, and to ensure that ductility, that should be less than 0.42. And this goes back to the idea, here, you can see here. So approximately, he said, if you look at this, it means that, that the steel has reached about twice epsilon y. If you look at it, if you draw it ultimate, and you would see that this ratio. So this is about ductility, okay, about making sure that the failure mechanism is a type of failure where you would guarantee that it will fail the way the code wants it. And there's another approach, like we said before, we had that before we had the capacity should be like 20% above a cracking capacity. Here, we're saying the should be at least 30%. Minimum value should be either equal to mcrack or about 1.33, 33% above the factored loads. So that's the FMN, should be greater than the minimum of the two, okay? Before we had it as 1.2 mcrack, right? 20% above mcrack. But given these two, okay, the FMN should always be larger than the cracking moment. And here's the equation given for the cracking moment, right? This is the equation given. It has many forms, but this is the equation that is given for that one. Okay, and I believe these are defined, gamma 1 and gamma 2 are defined in gamma 3, different one. Okay, and the rupture stress here, where F prime of C inside is in KSI. Okay, these are most of the limits in AASHTO. When you talk square root of F prime of C is in KSI. Okay, not in PSI. So this is a lot of can be a lot of mistakes on that. So this is the part that I wanted to basically cover, the different equations that control the pre-stressed concrete design. Of course, there are other equations, but these are the main philosophy of how we calculate the capacities, and there are other provisions. We will try to insert them in the example. So for this example, I'm just going to set it up for the afternoon session. And we have the same bridge that we did the deck design for. And we are using, this information, you've seen it before, but here, the concrete for the girder, the weight, the type of the tendon, all of this are important because when we calculate the losses, you need to know the humidity and all of that. And we're using the HL93. We have all the information about the barrier. We're going to design the interior girder for that one. And this is the girder. So we know what girder we are using. This is, if you look at the PCI manual, or many books have this information. These are standard sections, okay? About T, the 72 inches deep, PCI. And there are the AASHTO girders, and also, which is very similar, but those are, popular because they are produced by the producers a lot. Oops, sorry. So the first thing you want to do is, now we have the thickness of the slab. You want to try to find what is the geometric properties of the girder by itself and the girder as a composite with the deck slab. Now the deck slab, there used to be equations that to get the effective flange width, okay? However, in the new code, that changed about maybe 12 years ago, that we take the full depth of the spacing as your effective width. The average spacing of the girders, in this case, it's 9 feet. So that would be the slab, the effective slab. This is what we call the effective flange width, okay? Which is 108 inches. So you do all of those. These are provisions in the article. If you look at this article, it changed in maybe 14 years ago even. And so basically now, when you are talking about this, most of our equations are applicable to isotropic section, means it has the same properties. So we gotta transfer the concrete of the slab to the same concrete of the girder. And you know how to transform that. You find out what is the modular ratio between the concrete deck and the concrete slab, which is here, and the modular ratio. And you can find E, and if you have it, or you do both equations are related. E is related to the F prime of C, so you can come up with this 0.8. That means the depth 108 inches. If I want to use it as concrete made as the same girder, I have to reduce it by 0.8165, and I will get 88.182. All right. We checked this. We have an internal program. I checked it, and all the values are correct, more or less. So there are some small difference, but it's all within the tolerance values. And you find the center. You have all the girder center, the composite girder, CG of the girder itself. So obviously, when you put the slab, the CG will move up, right? So the CG is moving up, from here to here of the composite girder. This is the center of the slab. You can determine, and then you can do the area of each component, and then you can see the moment of the area. You can find the distance to the CG. You can take moment of areas, and you can find the moment of inertia for the composite girder at the end. And then you can find the CG, all of this information, all of these you will need, as top, as bottom, all of them for composite, for the girder alone. Because when you're finding the stresses, as you know, in prestressed concrete, what I showed you was the ultimate capacity. What I didn't show you was that when you're doing design, you're not designing based on ultimate, okay? And we will show you in a minute how you can do that using the feasibility domain, which is based on 4 stress inequality equation. Okay? I'm cognizant of the time. I think I have maybe 5 more minutes. So we'll start from when we left or afterwards. So here, are there any questions up to this point? So this is basic, geometry and bookkeeping of what the composite girder properties, the moment of inertia, the area, all the geometry that you need. Because when you start using the 4 stress equations, in prestressed concrete, for those of you, if you haven't had prestressed concrete, it's really an interesting, you have to make sure that the stresses, when you pre-stress the girder, it will camber up, the pre-tension. So you gotta make sure that the stress on the top of the girder in tension is less than what the allowable, because if it's not, then it might crack. You don't want it to be cracked. And the same thing in compression on the bottom at service. So there are 4 allowable stresses, at service, 2 at service, and 2 at, transfer or initial. And each, you gotta make sure that you satisfy those. This is how you make sure your design is adequate, okay? The ultimate capacity is conforming to the fact that when you design the beam based on your service limits, okay, or working stress approach, you satisfy also the capacity or will not fail. So that's what the equations I've shown you. But I should have shown you the way we do the actual, but it is in the example. So we will cover it that way. So now you need to let's calculate dead load, dead load for the girder and for the slab combined. Because remember, again, this is driven by the fact that the reason we separate those is by the fact that the load factors are going to be different for dead load and different types of dead load, right? And so sorry. So when you're doing the girder dead load at release, okay, the reason we do it there is because the girder is acting alone. It's not composite yet, right? So the stresses, when the girder is by itself, there's no slab on top, it will behave differently when there is composite with the deck. So the stresses are going to be different that you got because the inertia is different, and the loads that you're applying are different. So those are for the girder at release. Then you do the girder dead load at final stages, meaning, and we're giving here the equations at the moment, the equation in terms of X, because at each section for precast concrete, although we design at the maximum moment section, but the tendon profile might not be straight. It might be parabolic. It might be draped 2 points, heart at 2 points. And so you really need to take different sections because the tendon, the force, the pre-stressing force might change over the length of the beam. So therefore, you got to take different sections. And the best way to do it is keep your moment and shear as a function of X, and then take them, for shear, as you remember from reinforced concrete, there's a critical section for shear, where shear, some distance from the support. So you got to take that section for shear. So all those sections, we will highlight them in the next, the afternoon part. And, so you have to make sure to do the bookkeeping of different sections. But the analysis applies at different section is the same. The methodology is not different. The numbers will be different because the moment and shear, they interact and they're different. That the moment is maximum, let's say, in the midspan, but the shear is maximum at the support. And there's a variation of the shear between the two and the moment. So you gotta for every location, you have to make sure that usually, especially at the key points. So if you have a tendon draped at 2 points, so okay, between the 2 points is the same, the maximum moment, but you have to take one section at the drape point, one section outside of it, and then you'll be able to cover most of the impact of the dead load. And this is for non-composite. Then you add the composite dead load, you add the barriers, and then you add the future wearing surface. Why do we do it separately? Because again, the live load, the dead load factor, the load factor for dead load is different in every case. So when you are applying this dead load moment, you're gonna apply the 1.5. When you're applying the barrier and the slab, you're gonna apply 1.25. Are there any questions up to this point? And then, so now you estimated what are the loads, dead load mainly. Now you're gonna figure out, how do I do the live load? I have a truck, the HL93, and I wanna apply that. I can find the moment on the span, simply support span, I find the maximum moment. How do I distribute that lane moment from 1 lane or 2 lanes? Depending on the case that I'm considering, I'm gonna have to use the girder distribution factors. And let me stop at this point. We will pick it up from here in the afternoon, and we will be back, I think, if there are no questions, we will be back at, I believe, 1:30, right, Checo?
Yes.
Okay. So are there any questions up to this point? I do apologize. I mean, this online setup doesn't allow the questions and answers. I think that would have been if it was in person. Usually we allow people to do their own work in the workshop. That's part of the training. But unfortunately, we have to do it this way. We were thinking that will be in person at some point, but we want to commit to doing this more often. So I believe that this could be an annual thing if needed. And every year we can, do different, more advanced topics. And it could be load rating, it could be other things that whatever the DOT needs, we would like to help with that. So with this, I would like to thank you all for your attention. And I look forward to see you at